All right, here's probably the most powerful use of a system of equations, and that's when you're solving applied problems. We've done a few in the other sections, but here we'll do three more. So essentially we want to look at maybe a total value or mixture kind of problems, and also a problem involving motion. So just a few examples. And there's lots of other examples in your textbook too. The key to looking at any of these problems is to look for two different relationships. Using a table like I've done in this question and the next two questions is a really useful way of setting up those two equations. So in this one, it looks like I'm going to have an equation for the number of shirts, and I'll have an equation for the cost of the shirts. And then I'm not sure if I need this total cost line in there at all, but I'm going to be setting up two equations. So let's read. Biking clothes. A bike shop sells biking shirts with or without pockets in the back. Of course, the ones with the pockets in the back are the best. They let you put your camera in and goodies and that kind of stuff in. Okay, shirts with pockets sell for $19.50 each. Okay, cost of shirt with pockets, $19.50. Okay, shirts without pockets, $18.95. There's not much difference, eh? Might as well buy one with a pocket. Anyway, if total sales for 30 bike shirts total $572.90, so that would be this. I'm not sure if I put that here or should I put it down here. Well, let's see. How many? I'm just wondering where I put that number. I don't know if I'd put it here or here. Let's see. If total sales for 30 bike shirts. Oh, so there's 30 bike shirts, 30 total. We don't know how many there are with. Let's call it X. We don't know how many without the pocket. We'll call that one Y. I guess the total cost, I'd probably put that other number down here. The total cost of one's with will be whatever the cost of the shirt is times by how many shirts there are. So the total cost of shirts with a pocket would be 1950x. And the total cost without would be 1895y. Then my total is the total of this one and this one, they say is 572.90. Okay, I've got two equations. X plus y is equal to 30 and 1950x plus 1895y is equal to 572.90. Okay, two equations. I'm going to now do the same process as we did in the last questions. Where do you get the values of x to be the same? So in this case, I would multiply 1950 by the top row, coming up to 1950x plus 1950y is equal to whatever 30 times 1950 is. Okay, that'd be for my top one. And then I'd write the other one down below. 1950x plus 1895y is equal to 572.90. Now I have two equations. X's and y's are lined up. The x values are the same. They're both the same number. So I'll subtract the equations. This one minus this is 0. This one minus this is about 0.55y is equal to, and whatever that comes out to. And you just proceed, you just proceed on just the same as we've done all the other questions. This one has decimals in it, but it's the same thing. Let's turn our attention now to one where I have a mixture of something. And again, a table is a great way to help you organize your equations. My trail mix consists of almonds and Smarties. That sounds like a good trail mix. I maybe would put some raisins in there too, but um, don't want to mix up our question. We could do that in the next section where we have three variables. Okay, if almonds on their own cost $9 a pound, okay, just a second. Almonds, $9 a pound. And Smarties cost $8 a pound. How much of each type should be used to make a 20-pound blend? Oh, so weight of almonds and Smarties is 20 altogether. So I don't know how much almonds and how much Smarties there are. Let's call this one X and this one Y. So, and they says that sells for $8.40 per pound. So this one, I'm not sure how much this would cost, eh? Well, this one would be, the total cost would be 9.00x. This one would be 8.00y for the total cost, but I don't know how much this or this I have. But then they say 8.40 per pound. That doesn't really, it doesn't seem like it should go in this line. I'd probably think that that 8.40 would be somewhere up here. I'm just thinking about that. Notice that all of this playing around, thinking, well, try this, try that, that's important. That's an important part of figuring out questions. I know for sure I have one of these as x plus y is equal to 20. So I know x plus y is equal to 20. But now I'm not too sure about the other equation because I don't know, like this 840, there's no variables in here. I can't use, I'm wanting to do something like this. 9.00x plus 8.00y is equal to something here. But this has to be a total cost. But you know what? They say it's 840 per pound, but they also tell me that there's 20 pounds. So really the total cost here is going to be 840 times 20. So this would be like 1,668 bucks, somewhere on in there. I'm just doing that off my head, so I'm not too sure about that. But yeah, that would give me the total cost there. And then that fits in there nicely. Two equations, get x is the same, subtract the equation, solve for y, solve for x, etc. Okay, just like we did in the last question. That was the tricky part right there, is getting that total cost. One more. This one involves motion. Same kind of thing though. Notice I've got a pretty little table set up, ready to go. Motion formula, so here I have a motion formula. Distance is rate over time, or your velocity or your rate is equal to the distance divided by the time. Just a formula that is used quite frequently. So it says a cyclist leaves Lethbridge traveling east at 35. An hour later, cyclist leaves Lethbridge traveling at 45, also traveling east. So the question is, how far away from Lethbridge will the faster cyclist overtake the slower cyclist? Now, if the one overtakes the other one, they're looking at how far that is. When the one overtakes the other one, the distance for both the slow and the fast cyclist will be the same. And often in motion questions, that's what you do, is you look for the thing that is the same. So in this case, the distance for both the slow and the fast guy, I'm calling d. Rate of speed, the slow guy, he's going 35. That's actually very quick, but it's not bad. The 45 is, of course, quite a bit faster. Okay, so those are the rate of the speed. And then the time. I don't have a time. Oh, but they say an hour later. An hour later. So say if I said the slow cyclist, say I'll give him a time of t. If the faster guy leaves an hour later, that means his time is short an hour, right? Less than an hour, or 1 hour less than this guy. So his time would be t minus 1. Okay, two equations. I can use this formula up here to figure them out. I'll maybe get you started a little bit with this one, but it's the same kind of thing that we did before. We might use substitution in this one though. Okay, so distance is equal to rate times time. So distance is equal to 35 times by the time. So that's for the first row. Second row, distance is equal to 45 times by t minus 1. Okay, so if the distances are the same, notice this one, it's sort of set up good for substitution instead of elimination because I have solved one of the variables for already. So here if d is equal to this and d is equal to this, really what I can do now is if I want to know where they cross, what I can simply do is let the one side equal the other side, just like that. So if these d's are the same, it means that this must be equal to that. And then solve. So 35t is equal to 45t minus 45. Bring the t's over to this side, so it'll be 10t is equal to 45, and therefore divide both sides by 10. Therefore, it'll be about 4.5 hours before the one cyclist catches up to the other cyclist. About that. Um, yeah. So it's probably be, I don't know, Medicine Hat or so before, if they left Lethbridge and headed east, probably Medicine Hat or somewhere around there they would meet up. So those are some applications of using system of equations to help you solve the problem. Okay, try some questions in your book. If you have questions, call your instructor.